Okay, so we talk about network flow or flow network. So, what is the problem? Problem is we have given a graph. So, this is the definition. So, this is called a flow network. Is a directed graph or diagraph directed graph G comma E with two vertex, distinct vertex, which is called, one is source, another one is called sink, with two distinct vertex, distinguished vertex vertices S and T. This is called source, S O U R C, and this is called sink. And each edge, there is a weight associated with each edge, and that is called capacity. So, each edge UV has a non-negative capacity. So, weights are non-negative. Non-negative capacity, that is C u comma V, and between, if there is two vertex where there is no edge, then we define the capacity to be 0. So, if u comma V is not a edge, then we defined as C u V. This is the convention, there is no edge. So, there is no question of capacity. So, this is called flow network or flow graph. So, basically we will take some. So, basically each node. So, if we have u v, so this is a directed graph. So, if there is a edge from u to v, then there is a capacity, the value, a integer, non-negative value. So, we will take an example. So, we will take such an example of such a flow network. So, it is basically a directed graph. So, let us draw a directed graph. So, this is the source and we have the edges. These are the direction. This is a directed graph, these are the vertices, these are the edges. So, we have a, then we have here, here, then we have a edge over here, we have a edge over here. Okay, so, this is the sink, this is the source, that is the sink, and this is the directed graph. Now, we have to put the capacity. So, suppose the capacities are, so 3, these are all non-negative integer, 2, 1, 3, 1, 2, 3, 3, 2, 3, 2. Suppose these are the 2, 3, 2. Suppose these are the capacity. Okay. So, now we defined a network positive flow. So, this is another definition. So, a positive flow, on G, on this network G, is a function P, which is basically V cross V to R, satisfying the conditions, three conditions. First condition is called capacity constraint. So, we want to flow some current. So, say this is a current, these are the capacity of each wire. Now, we want to flow some current. Now, obviously, if the capacity is 3, then we cannot flow the current more than 3. So, that is the first condition. So, this is called capacity constraint. So, for all u v belongs to V such that, so this flow, this positive flow must be positive and it must be less than C u v. So, if we have two vertex u v, if this is u v, now this is C u v, now we want to have a P u v, we want to define a P u v positive flow. So, such that, so if the capacity is so such that it should be less than the capacity, because we cannot send more current than the capacity. So, that is the idea. Okay. So, this is the capacity constant. So, we cannot send more than the capacity. So, the second condition is called flow conservation. So, it is basically number 2. It is basically telling if we take any vertex other than sink and source. So, flow conservation should be 0. So, that means we are not storing any current, we are just passing the current. So, in other words, suppose this is U, this is a node which is not source and not sink. Now, there are some edges coming over here and there are some edges going out over. So, this is the coming flow, this is the current coming to you and this is the, so there are some more edges, this is the current going from you total. So, this difference should be 0. So, that means whatever current it is taking, it should distribute. So, it is basically it is not holding any current. So, it is just a distributor sort of media, I mean it is just a middleman just. So, this we have to write in a mathematical form. So, this is basically telling for all u which is not a source or sink, summation of P of u comma v. So, this is basically V is belongs to. So, this is basically the current which is coming from. So, u so this is basically current which are going from u to V. This is V 1, V 2, V 3 like this. So, these are the all vertices which is just basically outgoing vertices, this sum. Then minus the sum of the capacity V comma u, this is. So, that means this telling this is the all the vertices V I 1, V I 2 which is basically. So, this is basically sum of all this. So, whatever current we are having, we are passing that. So, this sum should be, this difference should be 0. So, flow conservation. Okay. So, we are not any middle nodes other than source and sink are not conserving any current, I mean it is just passing all the currents. So, this is sort of Kirchhoff's current law. So, whatever current is coming, it is just going out. Okay. So, we are not holding any current in the middle point. So, this is the definition of positive flow. If there are two conditions, one is the flow the P of u v should not be more than the capacity, and in the middle node we should not have any conservation of the current. Okay, now, let us take an example of the positive flow on this network. So, this is a given network, flow network, where capacities are given, and this is the source and that is the sink. So, now we want to have a positive flow on this network, which satisfy these two conditions. So, let us try to have that. Okay, so, this is basically capacity. So, we can have something like one flow on this, then 2 is the capacity, we can have at most 2 flow, this is the 0, okay. Then this is 3, so we can have 1. So, this is the basically positive flow. This is basically positive flow and this is the capacity. So, our flow must be capacity of that direction. So, our flow must be less than that capacity. This is sort of current passing on this wire. Okay, now, let us give some flow on the other edges. So, this is say 2, this is say 1, this is say also 2, this is say 1 and this is 2 and this is 1. So, this is satisfying the first condition. Everywhere if you check every node, suppose this is u. Now, if this is u and this is v. So, every node the capacity the flow positive flow is less than the capacity. So, that first condition is satisfying. Now, the second condition is if we have to take. So, the consumption current consumption. So, that consumption flow consumption must be 0 for any intermediate node which is not S and T. Suppose for example, this node. So, this node has what is the flow consumption? So, this node this is the flow coming. So, 2 is coming flow and then 2 and then this is another flow is coming 3. So, basically, so this is u. So, what are the flow coming? So, 2 this is 1. So, total flow is consumed. So, 3. Now, any other node is incoming node incoming vertex H? No, and the going is basically this one and this one and this one. So, this is 0, this is 1, this is 2. So, this sum is 3, this sum is 3. So, no current consumption. So, Kirchhoff's law is satisfied. So, that second condition is satisfied. So, this we can verify from any other node. Suppose this node, for this node suppose this is our u. For this node what we have, how many are incoming? So, this is u, incoming is this 2 and another 2, this one and no more. So, 4 total 4. And what is the outgoing? Outgoing is this one 1 and this one 1 and this one 2. So, 4 this is 4, this is 4. So, incoming and outgoing flow positive flow is same. So, this is satisfied. We can verify for other vertices also. So, this is a positive flow. Okay. This is a positive flow. Now, we want to define the value of this flow. What is the value of a flow? So, value of a flow, value of a positive flow is the net flow which is outgoing from S. So, this value is basically is the net flow out of the source. Yes. So, that means, so what is the net flow out of the source? So, that means, this is basically all the outgoing vertices, outgoing edges from S. So, this is basically P of S comma V minus if there are any incoming edge from to S minus summation of P of V comma S. So, this is the net flow. So, P of S comma V minus P of. So, now for example, here. So, what is the net flow? What is the value of the flow? So, value of the flow is, so sorry, not net flow, value of the flow. So, these are the flow going out, this one and this one, and this is the flow coming in, but this flow value is 0 and this is 1, this is 2, 3. So, value of this flow is 3. So, the value of this flow is basically 1 plus 2 minus 0, 3. Okay. So, this is the value of the flow. Now, is this the maximum flow and this is the value of the flow. Now, this flow, so what is the flow at t? What is the value of the flow at t? So, here, so this is 2, this is 3. So, flow at t is 1. So, whatever current we have passed here, that is we are consumed here. So, that means, and in between they are basically the intermediate node, they are just passing the current, not holding any current in their there. So, this is basically the flow. Now, we want to define what is the max flow. Is this the maximum current we can flow in this network? That is the question. Is this the 3 is the maximum flow, maximum positive flow we can pass into this network. So, that is called max flow problem. So, that problem is referred as max flow problem. So, we just define that maximum flow problem. So, we have given a flow network G. So, this is the definition. Given a flow network, this graph G V comma E and the capacity vector, find the flow of maximum value. So, flow of maximum value. So, that is called max flow. So, this problem is called max flow. So, we have given this, for example, we have given this graph and we have a flow, this is a flow P. So, now is this a max flow? Can you do more than this? Can you pass more current than this? That is the question. So, can you try to pass more current than this? I mean more value on the flow. So, let us see. So, this is the flow value of this network is, I mean positive flow is 3. So, can you pass it 4 like, okay, let us see. So, here we cannot pass more than 2, but here we can pass 2 or 3. So, let us try with 2. So, if we pass 2 over here, then this may create problem, because this is consuming how much 2 3 2 3. Now, it is passing. So, if we just make it 0, so we make it 0 and then, so this is basically now we can pass it 3. So, this consumption is basically 2 and here 3. Yeah, so 2 and here 3, we can pass this 3 because capacity is allowing us to pass 3. Okay. And then what we do? So, we have 1 over here. So, we can instead of 1 we can pass 2, we can pass because capacity is 2. That is it. So, this is the way we just pass this current, this. So, this is the way we can pass 4. Now, is this the maximum? Can we pass 5? Because this is 3, this is 2. So, this capacity is outgoing capacity is 5. So, now question is, can we pass 5? Oh, so that we have to check. So, that may not be possible. So, we can check that, you can check that is not possible. I think 4 is the maximum flow value. So, the max, so 4 is the maximum flow value. We'll have a, so we'll see how we can get that. So, the value of the maximum flow is 4. We cannot get 5. I suggest you to verify that. Okay. Okay. So, now how we can get this maximum flow? So, for that we need to do some theorem and some more definitions. So, first step we are going to do what is called flow cancellation. Flow cancellation. So, what is that? Without loss of generative, the positive flow goes either from u to v or v to u. Positive flow goes either from u to v or from v to u. So, that means, if we have u v like this. So, suppose suppose this is the example, this is u and say this is v. So, here both the direction positive flow are going, because from u to v we have a positive flow 2 and from v to u we have a positive flow 1. So, this we want to do some cancellation. So, what we do? We make it 0 and we make it 1. So, that means, so net flow, this is sort of net flow. So, net flow is remain same, it is basically 1, because 2 was going, 1 was coming. So, that is, so we can make it 0. So, positive flow without loss of generative, we can assume the positive flow is going only to the one direction, because if we have a flow in 2 direction, we can cancel 1, I mean which is the lower one. So, we can make it 0 and we can reduce the flow in other one. So, that is what we did. So, this is what we did. So, this was 2, this was 1. So, we convert into this V u. So, we make this 1 and we make it 0. So, this is referred as flow cancellation. Okay. So, we are cancelling the flow, that means, we are allowing the flow positive flow to from only one direction, not for the both direction. Okay. So, net flow from u to v is in case 1, because earlier also net flow is 1, now also net flow is 1. Okay, so now we want to do some notation simplification of this. So, we want to define the net flow. So, we want to define the net flow. So, let us run this. So, this is the notational simplification. So, instead of positive flow, we are just now interested in the net flow. So, net flow is idea is, so the idea is, because positive flow we have both the direction. Now, without loss of generative we say that we can cancel the one direction flow, and then that direction, one direction is 0, another. So, that is the net flow from u to v, and from v to u, that minus of that. So, that is the idea. So, idea is work with the net flow between two vertices rather than the positive flow, rather with the positive flow, because we can cancel the one direction flow, because net flow ultimately we are looking at how many flow we are passing. So, that way this net flow is, this is some sort of simplifying we are our thing. So, we have a positive flow, we will check these two definitions are same. So, we haven't defined it, in the next class we will define this what is the net flow, and then we will see the how these two definitions are basically equivalence. If we have given a positive flow, we can have a net flow. If we have a net flow, we can define the positive flow. So, that we will discuss in the next class. Thank you.